Let's talk about related rates. Let's suppose that we have this relationship of x and y. Okay, we've got y equals x squared. Now, we're saying, okay, x is the independent variable and y is the dependent variable. And we might want to find dy dx. Well, that would just be 2x. No problem. That's because we've got the input x and the output y. What if, however, that x is itself dependent upon some variable t and y is dependent upon some variable t? Okay? X and y are both functions of t, and we want to go through here and differentiate. Well, what would that look like? How would that affect our differentiation? Well, now we've got the chain rule involved, and we're going to harken back to our implicit differentiation. Now, so let's think about this. When I differentiate y, I'm going to call that dy dt, right? Because I'm differentiating with respect to t. See, y is a function of t. Over here, so that's this, the derivative of y, dy dt. Now the derivative of x, I'm going to use, remember how we do this with implicit differentiation. What we did for the y's, tacking on a y, differentiating the y's and then tacking on a y prime, we're going to do that with the x. This is 2x times dx dt. Okay? So notice the difference here. So in other words, the chain rule is at play here. We differentiate the outside and then times the derivative of the inside. Take the derivative of x squared, bring out the 2, the power rule, multiply by the derivative of the inside. And there it is. So there's what our derivative would look like then. Notice it's a little bit different here because we're saying x and y are both functions of some third variable t. Now, let's suppose further that we're given some information. Let's suppose that we're given, here's some things we're given. We're given that x equals 3 and dx dt is equal to, let's say 5. And what we want to find is dy dt. In other words, what we want to do is we want to find, we're given the rate of change of x with respect to t, we're given the value for x, and what we want to find is the rate of change of y, dy dt, with respect to t. So we're given this bit of information, and what we do is we go back and we plug in here. So we've got dy dt equals 2 times 3 times 5. And that would be 30. So look, we're given this relationship up here between x and y. And based on that relationship, we can then find a relationship between the rates, okay, the related rates. We find this relationship, or relationship between the variables, and then we find this relationship between the rates of change. Okay? Yeah. So let's think about this one. Let's suppose that a equals pi r squared. And we're told this, that dA dt is equal to, let's say 4, whatever units, when r is equal to 3, and we want to find dr dt. Let's suppose we're given this situation here. We want to find dr dt. Okay? So we've got the relationship here, a and r. We know how they're related. What we want to find is, well, how is dA related to dr? See? This relationship, and we want to find this relationship. How is dr and dA related? Well, let's see here. Let's differentiate. So we've got dA dt. That's that, derivative of a. And then we differentiate this side. 2 pi r, but wait a minute, we're not done. Tack on the derivative of the inside. See, we're using the chain rule. Okay, now let's see if we can plug in everything. In place of dA dt, I'm going to put a 4. And then over here we've got 4. Well, we've got, sorry about that. Over here we've got 2 pi times r. R is 3. dr dt. Okay, now we're almost done because they want us to find dr dt. Well, we're almost there. So here I go. I'm going to divide, and I'm going to get dr dt is equal to 4 divided by 6 pi. Yeah, that's it. So our final answer is 2 will go into 4 2 times, 2 will go into 6 3 times, so 2 over 3 pi. So the idea is we're given a relationship like this, and we want to then use that relationship to find how the rates are related. And then we can solve the problem. Now, let's look at this. Let's look at another one. Let's suppose we've got x squared plus y squared equals z squared. X squared plus y squared equals z squared. And we're given some information here. Let's suppose we're given that x equals 3 and y equals 4 and z equals 5. And we're told this. We're told that dy dt equals, let's say, we'll say 5. No, let me not let me not say 5. I don't want to repeat these. Let's say 6, and let's say dx dt equals 2. Something like that. And what we want to do is we want to find dz dt. That's what we want to find. Okay? So let's look at how this situation would work. I've got the relationship between the variables here, and I want to find how that dz dt is related to dy dt and dx dt. So I do that with differentiation. So I've got 2x, and let me just call it x prime, okay? Plus 2y, y prime, and let's just understand that this is with respect to t, equals 2z, z prime. Okay, now notice all these 2's will cancel out. So I've got x prime plus y prime equals z prime. And now I can put in my information here. Notice I've got x is 3 and x prime is 2. So this is going to be 3 times 2 plus, let's see here, the y is 4 and the y prime is 6. Z is 5. And all we have left to do is figure out what z prime is. So this is going to be 24 and 6. That's going to be 30 equals 5z prime. And then we just divide. So 30 divided by 5 is 6. So there we have our z prime. Okay, so this kind of gives you an overview of how we use related rates. And we're given a relationship, and then we use that relationship to find a relationship between the rates of change. So let's look at an example of how we might use related rates to solve a math problem. Let's suppose that a pebble is dropped into a body of water, and it forms this circular ripple. And you notice that whenever the radius of that ripple is 2 feet, it's expanding. The area is expanding at 5 square feet per second. That's how fast the area is changing. And what you want to find is the rate at which the radius is changing at that point. Okay, so notice what we're given here. We're given, okay, so let's just write down what we're given. Okay, we're given dA dt whenever the radius is equal to 2 feet. And we're given that that is equal to 5 square feet per second. That's what we're given. And what we want to find is dr dt. That's what we want to find, dr dt. So I need a way to relate the area and the radius for a circle. Because what I need to do is ultimately I want to find how is the rate of change of the area related to the rate of change of the radius. But first, I need to know, in a circle, is there any mathematical relationship that I can find that contains both the area and the radius? And there is. There's the area equals pi r squared. Well, if that's the case, and it is, then we can find how the rate of change of the area is related to the rate of change of the radius. So let's do that. Here we go. We've got dA dt equals to 2 pi r and then dr dt. See? Because r is a function of t. So we've got that implicit differentiation thing going. So now, at this point, I can just put in what I've been given here. I've been given the 5, so I can put that in. Okay, so I've got 5 square feet per second. That's what I'll put in for dA dt. And then over here, I've got 2 pi, and in place of r, I'll put 2 feet. Like that. And then dr dt. Now, I think I've put in everything I need to, right? Okay. Now, let me clean this up a little bit. I've got 5 square feet per second. Let me make that a little more legible. Okay, 5 square feet. And over here, I get 4 pi feet dr dt. Okay, there we go. Now, only thing I have to do to finish up is divide. So I've got dr dt is equal to 5 square feet per second divided by 4 pi feet. Yeah, that's it. And of course, this would wind up being 5 over 4 pi feet per second. There we have it. Okay, so that answers that question. And notice, remember what we did. We first of all found a relationship between area and radius, and then we use that to find the relationship between the rate of change of area and the rate of change of radius. Now, let's suppose that we have a situation like this. Let's suppose that maybe we have, now remember, so we knew that this area equals pi r squared. Now let's suppose that there is a sphere, okay? So we're switching to a different problem now. And let's suppose this sphere is being compressed. Okay, so it's being compressed. And it's being compressed at this rate. It's being compressed at, oh, let's say 10 cubic feet per second. And that's occurring when the radius is equal to, oh, let's say 4 inches. I mean, not 4 inches, I'm sorry, 4 feet. 4 feet. Okay, let's suppose that. And what we want to do is we want to find dr dt at that point. In other words, we have this sphere being compressed at 10 cubic feet per second when the radius of the sphere is 4 feet. So we want to find dr dt at that point. So we need a relationship between the rate of change of r and the rate of change of the volume. But first of all, before I get to that point, I need to go back and say, okay, well, how can I relate V and R together? Well, I've got this sphere. Okay, let's look at another one. Let's suppose that we've got a sphere. And it's being compressed at, let's say, 10 cubic feet per second. When the radius of the sphere is, oh, let's say, 20 feet. 20 feet. Okay? And what we want to do is we want to find dr dt when that's happening. Okay, now let's write down what we're given. We start off writing down what we're given. We're given that dv dt, that's part of what they gave us, when r is equal to 20 feet, is equal to 10 cubic feet per second. Now, you got to be careful, because this is different from the previous problem where we had a circle expanding. In other words, the rate of change was positive because it was getting bigger, right? It was growing. The area was growing. Well, this volume here is not growing. It's getting smaller. It's constricting. It's being compressed, right? So we're not going to have a positive rate of change. We're going to have a negative. The volume is decreasing. And when a volume is decreasing, that indicates you're going to have a negative derivative. So this, when they say it's being compressed, that means, you know, it's losing that volume. So it's negative 10 cubic feet per second when the radius is 20 feet. Okay, when the radius is 20 feet. And what we want to find is we want to find dr dt. Well, so I need a relationship between the rate of change of volume and the rate of change of radius. And to do that, I go back and say, well, I need a relationship between V and R. Well, we know the relationship between volume and radius on a sphere is volume equals 4/3 pi r cubed. Yeah, like that. Well, once we have that relationship, now we can go back and we can go ahead and start differentiating. So here's what we've got. We've got dv dt equals, let's see here, this is going to be 4 pi r squared dr dt. See? So because I just brought the 3 around using the power rule, the 3's canceled, and then 4 pi r squared, and then dr dt. Now I can start plugging in things. So here's what I've got. I've got dv dt. Well, I'm going to plug in the negative 10. Now I'm going to drop the units here. We know that we're going to end up with linear units, so I'm just going to drop all the units here and just calculate. We know we're going to end up, you know, we're going to have cube over here, and we're going to divide by square and get linear units. But let's just concentrate on the math here and So here's what we've got. We've got negative 10 equals 4 pi. In place of the r, I've got 20. Now, you always have to be careful you're in the same units. Like, you wouldn't want to have some units in feet and some in inches. You have to be sure you're in the same units, and we are here. So we've got 4 pi 20 squared dr dt. Yeah, there we have it. Now we can go through here real quickly and say, well, dr dt is equal to negative 10 divided by 4 pi times 20 squared. And that's going to be feet per second. Yeah, and that's how fast your radius is going to change. You work all that out. I'll just leave it like that. But that's how fast your radius is going to change. We found the rate of change of the radius.